inviting me to KAIST again, and nice to see some of you again. And today, as Sang said, I will talk about the phase transitions in random graphs. Before I talk about it, let me say some words about phase transitions in general. The phase transition in general deals with sudden global changes, and it appears in many fundamental problems in statistical physics and mathematics and computer science, such as Ising model or Potts model from statistical physics and graph colorings and random K-stat. Then in late 50s, Erdős and Rényi described so-called phase transition in random graphs, and it refers to a phenomenon that there is a critical edge density, and to which adding a small amount can change the graph structure and size of the components drastically. And since this seminal work of Erdős and Rényi, many different kinds of random graph models are introduced and studied. So in this talk, I will discuss several of them. First about the Erdős-Rényi random graphs, but then random graphs with a given degree sequence, and random graph processes, and finally random planar graphs. So let me start with the Erdős-Rényi random graphs, and the most famous and important random graph model is the so-called binomial random graph, GNP. In GNP, each pair of unordered pairs of vertices is joined by an edge with the probability p independently of each other. This probability p can be constant, but also it can be a function in n. Another important random graph model is the so-called uniform random graph, G and M. It is a graph chosen uniformly at random among all graphs with n vertices and m edges. Throughout the talk, the graph will be simple without having multiple edges and nor loops. These two models are, as you might guess or might not guess, are essentially equivalent. I will not define what do I mean by essential, but they are essentially equivalent if the number of edges in two models are similar. In other words, so in the uniform model, the number of edges is fixed by m. So if m is about the average number of edges in the other model, namely the n choose 2 times p, then two models are essentially equivalent. So you can study one model and translate the result in terms of the other model. The advantage of GNP model is the edge independence. Therefore, the analysis can be favorable. On the other hand, in the uniform random graph, the edges are sort of dependent, but on the other hand, it gives us a nice evolutionary point of view. You can imagine as m growing from 0 to n choose 2, so you can think of the evolution, sort of the evolution of G and M as m increases from 0 to m. And from that point of view, the evolution of G and M is quite well known. The almost complete picture on G and M is known. But in particular, when m is around n over 2, we can observe a dramatic change in the component structure, the so-called phase transition, which I will explain in the next slide. So let the number of edges, so through now I will focus on the G and M, but you can translate this result in terms of GNP. So let the number of edges m to be parameterized as c times n over 2. In other words, c denotes the expected number of neighbors of a random vertex. And Erdős-Rényi describes the following phase transition phenomena. So if the average number of edges, C, average degree C is smaller than 1, then AAS, which reads almost asymptotically surely, meaning that with the probability tending to 1 as n tends to infinity, all the components are of order big O of log n, and we call such a component small. Furthermore, each component is either tree or unicyclic. So they are very small, and also they are rather simple. And in particular, they are planar. On the other hand, if the edge probability C, the average degree C is larger than 1, then AAS, there is a unique largest component of linear order, while every other component is small. Small meaning the component of order and most log, big O of log n. And we call such a unique largest component of linear order the giant component. And this giant component is the unique component having at least 2 cycles, therefore having more edges than the number of vertices. And furthermore, if we delete this giant component out of the graph, the remaining graph looks as if we are in this range with different parameters. We have to reparameterize it. Nevertheless, the structure looks exactly the same as before. And we call such a range as the subcritical range, and this as supercritical range. In the study of phase transition, do I have it here? Yes. No, I don't have it now. So if you look at it, you can see that the average degree C around 1 is sort of crucial here. There is a dramatic change when the number of average degree goes from below 1 to the 1. And the reason why the average degree C equals 1 is so crucial is nicely explained by Kang. He used the so-called breadth first search idea from computer science and the so-called Galton-Watson branching process from probability theory in order to decide the size of the component containing a random vertex. So you fix your favorite vertex and you explore its neighbors and neighbors and neighbors. And there I said that as an approximation, one uses the Galton-Watson process. So let me explain what it is. The Galton-Watson branching process starts with a unisexual individual, and the number of children is an IID, Poisson random variable with the mean C. C is the same as the average degree in the graph. Now we start from a root node, and it has Poisson many number of children, and each of its children has also Poisson number of children, and they are independent of each other, and so on and so on. But then from the branching process theory, what we know is that if this mean C is smaller than 1, which means the average number of children is smaller than 1, then as you can expect, the process dies out with a probability 1. But this corresponds to a small component in GNM. Size here correspond, so here one should be a little bit careful, because in the graph, of course, when we explore its neighbors, we should not explore the already explored neighbors. Explore the neighbors of the previous vertices. On the other hand, in the Galton-Watson branching process, all the vertices are fresh. They are newly born. But so you have to fiddle around how you can really prove that this indeed is the case for the small component in GNM, but it can be done. On the other hand, if the number of children in each generation is larger than 1, or of each individual is larger than 1, then with positive probability, the process continues forever, which means that the size of the tree is infinite. But on the other hand, there is another way of translating this result to the giant component of linear order in GNM. Say it again. Here, the subtle difference is that in the Galton-Watson branching process, the total number of nodes in the process is infinite. However, in GNM, we do have exactly n vertices. But having a so-called sprinkling and so on, one can prove that indeed this corresponds to the giant component of linear order in GNM. In particular, the survival probability rho of the branching process is a solution of that transcendental equation, and this rho then corresponds to the probability that a random vertex corresponds to lies in the giant component. Yeah, this is about the giant component. We do know the average order of the giant component. Then you might wonder if there is any kind of limit theorem for this particular random variable which indicates the order of the giant component. Indeed, we can do. So let L of n denotes the number of vertices in the giant component after the phase transition. Then, as we have seen already, the average is rho times n. Furthermore, L of n satisfies the law of large numbers in the sense that this random variable is equal to its expectation, rho times n plus little o of n with high probability. Having such a law of large numbers, one might wonder whether L of n satisfies a stronger limit law, and indeed this is the case. Together with Berish and Goy-Auglan, I could show that the L of n, the order of the giant component, satisfies the local limit theorem in the following sense. The variance of the order of the giant is linear in n, and the constant depends only on the rho and the c. Then for any integer k, which is of the form, so expectation of L plus little bit of perturbation, which is big O of the standard deviation, so the square root of n, then the probability that the order of the giant hits exactly the integer k converges to the Gaussian probability density with the mean standard Gaussian density function with the standard deviation sigma. So if you give any integer value within this range, then I can give you the almost exact probability to that. Then another research direction in this phase transition study is the so-called critical phase. So in the previous slide, I showed you what happened if c is a constant and if c is larger than 1 or smaller than 1. But you might wonder what happens if the average degree c converges to 1. Yeah, so average degree is not anymore a constant, but it's a function in n which tends to 1. And then the question is how fast the size of the giant component changes depending on how fast the average degree converges to 1. Yeah, so in other words, we want to find the right scaling for this little o of 1. To do this, we need the parameterization. So let m, the number of edges, to be equal to n over 2 plus s for s little o of n. In this slide, it is exactly the same as this line. I rewrote everything in this terminology. But then, when you want to describe the phase transition more precisely, opening up the window, then what is crucial is to find the right scaling for s. Now, how should we scale it to see something different? And it turned out that it was proved by Balabash and Tomasz Uchak and Uchak, Peter Wehrmann, that the right scaling factor for s is n to the 2/3. So if s times n to the minus 2/3 tends to negative infinity, in other words, number of edges is for example like n over 2 minus log n times n to the 2/3, then AAS, with high probability, all the components have much smaller than n to the 2/3 vertices. So on the other hand, I go to here, if s times n to the minus 2/3 tends to positive infinity, then almost asymptotically surely there is exactly one component with much more than n to the 2/3 vertices, while every other component is rather small, like here. In the middle range, so in the critical phase, when the s times n to the minus 2/3 tends to a constant, for example, m equals n over 2, yeah, when lambda is 0, right? It includes the particular case as well, but it turned out that the lambda equals 0 is nothing particular. Yeah? Lambda can be any constant, like when m equals n over 2, or when m equals n over 2 plus 3 times n to the 2/3 behaves the same, namely the largest component has theta, some constant times n to the 2/3 vertices. from the first view, it's kind of rather strange why the lambda equals 0 does not play a special role. But indeed, this is the case. When you study phase transition, if you open up the window, then within the window, the behavior is the same. And this type of phase transition is universally observed in many kinds of random graph models. And this is the so-called mean field theory because of this right scaling n to the 2/3. And the physicists might have an explanation for that, but I am not a physicist, so I don't have an explanation, but they call it mean field theory. With the critical exponent 2/3. And in the giant paper, the Uchak-Knuth and Janssen, Knuth, and Uchak and Pittel prove many beautiful theorems on the giant component, but in particular, a relevant theorem for this talk is the following. In the supercritical range, when s times n to the minus 2/3 tends to positive infinity, then the order of the giant component can be written more precisely, namely, this is roughly 4 times s. Yeah, so here in this statement I said there is exactly one component with much more than n to the 2/3 vertices. But here you can refine it further, namely that the order of the giant component is indeed roughly 4 times s. Yeah? And it tells us the speed of the growth of the giant component. But then since this kind of seminal works, many different kinds of random graphs with constraints are introduced. Random graphs with constraints are, however, difficult to analyze because of the dependency of the edges compared to the GNP or GNM. And therefore, in order to study them, many different fields of mathematics and computer science and statistics get together to solve these problems. So, but why these random graphs with the constraints are so popular nowadays? One reason for that is,
Can I have that?
Yeah.
So for the last region, are there any other restrict conditions on
No. S is only this one, and little o for n.
Oh, S.
Sorry.
Okay.
So to be precise, because I copied and pasted, in order to be precise, I should have written in this manner. To be honest, so Sang-in has always very sharp eyes. And I should have written in this manner. This is better. Yeah, I just did the copy and paste, and then it's usually wrong. Because the reason why Sang-in is asking that perhaps is that if x is linear in n, so now in this range, then we are after the phase transition. Therefore, the size of the giant is linear, and this is indeed consumed there. So there is no sudden change there. So if we smoothly change s into linear in n, then we will have the similar result as before, like a row. You will be able to find this row as well, not this full. It will change according to the density of the s, and until that point, indeed, this is exactly 4 times s. But then, once s reach this linear, then there is also smooth change. But if s reaches like 1, so what is it? C minus 1, is it? Yeah, so this will be then 1 plus something else. So this, in terms of the C, we have seen this row function, and one can say that. In this giant paper, you can find all this kind of details indeed. So, returning to this introduction of the random graphs with the constraints. So, random graphs with the constraints, as I said, became very popular in recent years. So, one reason for that is that there are restrictions or constraints inherited from or imposed on complex networks, perhaps arising from real world, such as protein interaction networks or social networks or sensor networks, which I don't work on it, but it serves as a motivation. So, for example, like epidemic networks or some other complex networks, it has some feature, the so-called inhomogeneity, which means in the system of the network, or in the network, there are a few vertices of high degree, while every other vertices of low degree. But on the other hand, if you look at the GNM or GNP, what is the average degree of a random vertex is n minus 1 times p. And indeed, one can show that the degree of a random vertex is concentrated around its mean. So wherever we are, which vertex we look at, it doesn't matter. It always looks the same. Like in average, it does have a degree and roughly n times p. N times p, sorry, not n over 2, but n times p. So it's, in that sense, the classical random graphs are homogeneous. Yes. In order to somehow provide or circumvent this kind of difficulty or problem, a new graphs are introduced. One of them is the so-called graphs with a given degree sequence. Yeah, so it includes that particular inhomogeneous graph. So there, given a degree sequence D consists of D0, D1, 2, dot, 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 and we want to make them as to be something in the graph, in the sense that they represent the number of vertices of degree I. Therefore, there is such a condition. Furthermore, we want to have the proportion of the number of vertices in the graph that I will define later converges to certain constant as n tends to infinity. So it does not behave wildly. So we won't have them rather smooth. And there is other smooth conditions, which I don't want to specify. It's a kind of small details. Then, given B, we consider a random graph G of D, which is chosen uniformly at random among all graphs on n vertices, where there are exactly d sub I vertices of degree I. So d sub I is given by this sequence, and we want to have in the graph exactly d sub I vertices of degree I. Then it turned out that the phase transition in this new graph, G of D, occurs when the quantity Q of D, which is defined as the sum of I minus 2 times I times delta I, this was the proportion of the vertices of degree I, equals what? 0. But why this is it? So to prove this one, the idea is to use again a branching process approximation like in the standard random graphs. But however, here we should properly tune the number of children of each individual of the branching process according to the degree sequence, right? So before, roughly in GNP or GNM is the same. Number of children is roughly the average degree and roughly the degree of the vertex, unless we have revealed too many vertices. This is like binomial distribution with parameters n minus k, comma p, where k is the number of vertices that had been revealed already. And there we use the approximation, Poisson approximation of binomial coefficient, so that with mean c. Right? So all the vertices had same distribution, either in binomial to be exact, or Poisson as an approximation. But in the given degree sequence, it cannot be so, right? All the vertices behaves differently according to its degree sequence. So to realize this kind of a very simple observation or the definition of the random graph, we use the so-called random configuration, where we clone each vertex according to its degree. So the vertex degree of vertex V1 is 3, then we clone them 3, and so on. Then on the cloned vertices, we consider a uniform perfect matching. Okay, so these are perfect matching. Then when we contract the cloned vertices to the original vertex, like here, clone it, then the resulting graph is a graph with that particular given degree sequence. Yeah? What could be a problem of doing this?
Multiply edges.
Multiple edges and set groups, right? doing this, the danger is that we introduce, like here, multiple edges or self-loops. But on the other hand, one can show that with positive probability, and also second problem is that the multigraphs are not uniformly distributed. But the way of going around is indeed with positive probability, the resulting graph is a simple. Because because with positive probability, the resulting graph is simple. What we usually do is we prove everything in the configuration model and we translate it to the simple graph. Because we can condition on this positive probability space. This is how we usually do. So we will prove then, we will define this branching process approximation on this random configuration model. By the way, this is not defined by myself, but it was defined by Balabolobash and Wormald and Bender in the 80s. So it's a kind of typical method when you study any graph with a given degree sequence, then we usually make a detour via random configuration. Then we want to define the branching process on the configuration, so we have to reveal the so-called perfect matching edges. We sometimes call half edges, so no, not half edges, but perfect matching edges. So now, assume that the E is revealed at the current stage. And we want to determine what is the number of children of this particular vertex, to which the edge is incident. The edge E has been revealed now at the current step, and we want to study what is the number of children of that particular vertex that E belongs to. Then, easy to see is that the probability that X, the number of children of vertex V, equals I minus 1 is equal to the probability that V, the particular vertex V, is one of the DI vertices of degree I. In other words, E is matched to one of the I clones of a vertex of degree I. That's all the same thing. I'm just repeating the same thing so that you are used to it. Then, in terms of the numbers, it's nothing but, so there are DI vertices of degree I. We cloned each vertex according to its degree. So there are I times DI cloned vertices related to the degree of I, right? And we normalize it, so therefore this is the probability. So remember, delta I is the proportion of the number of vertices of degree I. So this is the probability. Having this probability, easy to see, is the expectation. Its expectation of X is nothing but this. So now we return to the branching process theory, and there the criticality was determined by its expectation, whether this is bigger than 1 or smaller than 1. So we have to determine when it becomes 1. The critical point of the branching process is when the expectation equals 1, so you do the algebra equals 1. Then this is equivalent to saying that this Q of D equals 0. And that's how we determine the critical point. Right? It's a calculation. And not exactly this branching process, but slightly different branching process. So this branching process is defined by myself and my former PhD student Tara Sayerstadt, but similar, but from my point of view, rather non-natural branching process was defined by Bolloy and Reed, and they prove the phase transition of a random graph with a given degree sequence as follows. In essence, it is analogous to the phase transition in a standard random graph. This is disguised, but if you look at it, the quantities and so on, this is exactly the same as what happened in the standard random graph. So the critical quantity was Q of D. This is sum of I minus 2 times I times the proportion of the number of vertices of degree I. So if this quantity is smaller than 0, then all the components are small. And on the other hand, if Q of D is larger than 0, then there is a unique component of linear order, while every other component is small. And the structure itself is also similar. And there, the components are either trees or unicyclic. And here, this unique component of linear order, namely the giant component, is complex, meaning that it does have at least 2 cycles. So now, having this result, you might wonder what happened in the critical phase, namely when the quantity Q of D tends to 0. So we have to have a sort of a measure how fast Q of D converges to 0. As this quantity looks rather complicated, we consider a more complicated thing, namely the so-called generating function. So let small q of x be the generating function related with this Q of D. So Q of x equals sum of Q I minus 2 times I times delta I times x to the I. When x equals 1, then this is equal to Q of D. Yeah? So to measure how fast Q of D converges to 0, we introduce a sequence tau sub n, which converges to 1. Then small q of tau n converges to 0 when converges to Q of D. Yeah? So this is how we go around. And as in the standard random graphs, the key point is that how fast delta tau sub n converges to 1. And it turned out that 1 minus tau n times n to the 1/3 plays the same role as this s times n to the minus 2/3. From the point of view of a standard random graph, in terms of number of edges, this quantity is the same indeed. So if this quantity tends to negative infinity, then all the components have much smaller than n to the 2/3 vertices. On the other hand, in the supercritical range, namely the 1 minus delta n times n to the 1/3, so you can imagine as s times n to the minus 2/3 tends to positive infinity, then there is a unique component of order much larger than n to the 3rd, while every other component is small. But then there is this another log n separation, that the lambda n shouldn't be too slow. It should be at least log n. But this is indeed due to the technique using this generating function technology. So if you avoid this generating function technology, then maybe you can erase this one, and it happened indeed the same year. The Jansson and Malvina Lucha could get rid of this log n separation using purely probabilistic method without generating functions. Then next I will introduce another different kinds of random graph model, the so-called random graph process. Is there any question for random graphs with a given degree sequence?
What was the tau in that? Yeah, tau n.
Tau n, what?
Yeah, tau n in the previous pages, 1 minus tau n times of something.
Tau n?
Yeah.
Tau n? Tau n, indeed, I disguised in this manner, but this will be the solution Q of tau n equals 0. So you can show that indeed, if you look at this as an equation equals 0, then one can find a solution tau n, Q of tau n equals 0. So that Q of D equals 0 in the limit. But then you can also prove that then tau n should converge to 1. Yeah.
So do we have any way to compute or approximately compute the behavior of tau n in terms of element?
Only this like this, only in this manner. Yeah. This is the same as like scaling our random graph in GNM like this, right? Then there, in a way, S is an input. I don't need to determine the behavior of the S because it's our input. So you can also think of this tau n as an input, to be honest.
Instead of solution of generation.
Yeah. So you can. That's why I put it this way, because the way how we prove it is the solution of something, but then it doesn't give us too much information. But if you do the analysis a lot, then this quantity should behave like this, and furthermore, it should behave like this. This is perhaps the answering your question in a different way, but anyway, you can think of tau n as an input. As an input, and then and so on and so on. Because then if you consider tau n as an input, then it determines the behavior of the delta i's, namely the proportion of the number of vertices of degree I, namely the degree sequence, you know. So you can think of as if tau n is part of the input data, the degree sequence. Yeah, thank you. Yeah. Are there more questions? If not, then I will move into the third part of the talk. It will be short, by the way, because I want to talk about the random planar graphs in more detail. A random graph process is a Markov process whose state space is the set of graphs that we want to study. So depending on your favorite model, you can define the random graph process. So in each step of the process, a single or several edges are added according to a prescribed rule. Sometimes you can also delete the edges. So as you wish, you can define a Markov process so that at the end you want to have the graph that you want to study, like triangle-free graphs or k-fold free graphs in the end. But then one of the famous random graph processes are defined so that we can substantially delay or accelerate the appearance of the giant component. So according to your favorite problem, you can define random graph processes. But I am personally interested in phase transition, so I'm particularly interested in that type of random graph processes. But if we're interested in random Ramsey number, for example, then there you want to avoid certain graphs like triangles or k4s, k5s, right? In order to determine, get the lower bound of the Ramsey number, then you have to define different process like triangle-free. But for this particular purpose, what is good is that the random graphs which evolves with the degrees, like giving degree constraints, or you favor the minimum degree vertices to be attached first, or the edges come in pairs and you can decide which edge I will add so that I can accelerate the appearance of the giant. This has been done for many years, starting from Akliottas and Tom Bowman and Alan Fries in Carnegie Mellon. And then last year I was visiting New York, and together with Joel Spencer and Will Perkins, we studied the so-called Bowman-Fries process, which is a particular case of the random graph process where the edges come in pairs and we select one with the minimum small degrees. And when you study random graph processes of that type, the key quantity that we have to study is the so-called susceptibility, which is the average component size. And also, if you think about this graph process, it somehow evolves by time. Because of that dynamic nature, one can set up so-called differential equations by looking at the expected change of a certain random variable. Then further, you can show that this random variable that we want to study in the end is sharply concentrated around its mean by using sub and super martingale. To illustrate this method, let me return to the standard random graph G and M, because it's easier to explain. And the number of edges is parameterized by t times n over 2. So before I used the constant c, right, to indicate the average degree. But now t to mean the time. So we let t be the average degree, but by the way, as a time t. Then the susceptibility, depending on t and n, given t and n, we define the susceptibility to be the average component size, the sum of the size of the component for each vertex divided by n, so average component size. Then we write it, we massage it a little bit, so we represent it as a sum of I times pi, the number of vertices in components of size I, divided by n. What is the interesting thing is that this pi is concentrated, there is a determinate function, small p sub I of t, independent of n, so that this random variable, big pi of t comma n, is equal to determinate function p sub I of t times n plus little of n with high probability. Furthermore, if you consider the generating function for this deterministic function of that type, then it satisfies the so-called quasi-linear differential equations. Quasi-linear differential equations. And studying the singularity behavior of the solution, f, one can study very fine behavior of the component sizes, like p sub I or c of vk. It gives us a way to study C of vk to be very, very fine. So like in terms of the kind of exponent, I can say the piece of I behaves as if it is like I to the minus 2/3 times some exponential constant gamma to the n. And having that, you can study a lot of different kinds of quantities, like what is the largest component, what should be the second largest, and so on. And for this type of variance of the standard random graph process, this term will be different. This is so-called homogeneous type, but if you modify your process, it will be more complicated here, not here. So here can be also complicated, but the trouble is to analyze these non-homogeneous differential equations. So then I will move to the fourth part, which might hopefully will be more interesting from a graph theoretical point of view, is the random planar graphs. A graph is a planar if it can be embedded in the plane without crossing edges, and we consider a uniform random planar graph denoted by P and M, which is a graph chosen uniformly random among all planar graphs with n vertices and m edges. Studying P and M, or random planar graphs, you might wonder, what about G and M, the standard random graphs? Isn't it simply G and M, same as P and M? Sometimes yes, sometimes not, depending on the edge density. When we were studying the phase transition in G and M, I already told you when M is strictly smaller than n/2, the graph consists of trees and unicyclic components. So it's a planar. So depending on the edge density, the answer is yes or no. Maybe G and M is the same as planar P and M, or maybe not. And this has been studied, of course, by these masters, Jansson, Knus, Uchak, and Pitel. And what they say is that, like in the phase transition, the number of edges should be parameterized as n/2 plus s, little of n. So if s times n to the minus 2/3 tends to negative infinity, it's the same as in the supercriticality for the phase transition. With high probability, the standard random graph G and M is planar. On the other hand, in the supercriticality, when s times n to the minus 2/3 tends to infinity, then with a high probability, G and M is not planar. In the middle, mid-range, when this quantity tends to constant, negative or positive, doesn't matter, even 0, and with positive probability, G and M is non-planar. So something interesting is going on in this critical phase indeed. And for that, to kind of study further what's going on in this range, what we do is we study so-called the internal structure of complex graphs. A component is called complex if it contains at least 2 cycles, which means the number of edges is strictly larger than number of vertices. But on the other, it's complex enough because in this range, the number of edges minus number of vertices tends to infinity. So it is rather complex. So we call it complex component. So we look at the internal structure of complex component. Because if we delete the giant, we do know from the G and M, in this range there will be a unique giant component, and if I delete it, the rest of the world is a tree or unicyclic component, therefore it's a planar. So the plan is that we consider only complex part, and to study that, what helps us is the so-called core and kernel of complex graphs. The core of a graph is a unique maximal subgraph with minimum degree 2. And the kernel is obtained from the core by replacing each path by a single edge. In other words, given a complex graph, we delete the trees out of the graph and replace each path by an edge. By doing this, we arrive at so-called multi-graphs whose minimal degree is at least 3. We call it the kernel. And in order to so-called generate or create a random planar complex graph, indeed we can reverse the procedure. So we start from a typical candidate of a kernel, which is a multigraph whose minimum degree is at least 3, and we replace some of the edges by paths, and we plant trees on that. Yeah, we plant indeed rooted trees, rooted forest indeed. And doing this, we observed, Tomasz Uchak and I observed that cubic planar weighted multigraphs plays a crucial role as the kernel. Why it should be multi, I explained already. By definition of a kernel, it should be multiple. But why should it be weighted? If there is a parallel edge, to replace this parallel edge by paths, we have to avoid overcounting. One way of doing it is weighting the edges. So this way. But cubic planar graph is dense enough so that one can apply the classical asymptotic enumeration method from analytic combinatorics. In other words, n structural graph theory. In other words, you decompose the cubic planar graphs into smaller parts and apply the Tutt decomposition theorems, and therefore you can represent the structure, the number of planar graphs with the cubic planar graphs as the solutions of the systems of equations of generating functions. And then having the system of the generating functions, you can analyze its singularity and singular behavior, meaning that you can determine the critical exponent, and then starting from that, you plug in back our graphs. So this is about the planar complex graph, and using that, Tomasz Uchak and I show that there are two critical periods in the evolution of random planar graphs. Now, in the standard random graphs, we have seen one single critical period, but in the planar graph, there are two. The first one takes place when the giant component is formed, and it takes place when the number of edges is around n/2. This is analogous to the phase transition that we have seen already, even twice. Yeah? For example, when the number of edges is around is m equals n/2 plus s, and where s is in this range, like here, then the size of the order of the giant component is roughly 2 times s. On the other hand, we have seen that uniform random graph in this range, the size of the giant is roughly 4 times s. So it's half the size. On the other hand, it was proved by Uchak and Biermann that uniform random forest, the size of the order of the largest component is roughly 2 times s. So in that aspect, random planar graph in that range behaves as if it is a forest. In that view, of course, in detail it's different, but in terms of the size, it's the same. Yeah. And furthermore, the PNM has the second critical phase when the giant component covers nearly all the vertices. Yeah? So imagine, so here we know that there is a giant component of this size, but if we go above n/2, so like m equals n/2 times 1.1, yeah? Then we can imagine that size of the giant is linear, but we add more edges, so that number of edges is much larger than n/2. Now it's nearly n. Yeah? So when this happens, then one can observe a second critical phase. So to be more precise, the scaling factor for t is n⁵. So for example, when t is about n⁵, much larger than n⁵, but much smaller than n, this n⁵ is due to technicality. So we believe that this can be replaced by n. Then the total number of vertices outside the giant, you delete the giant, the total number of vertices outside the giant is much smaller than n⁵. This second type of phase transition I have never seen in any random graph models that I know of. Maybe there are other random graph models, but this has not been seen. But how do I get this kind of strange exponent is due to the asymptotic number of cubic graphs. It highly depends on the asymptotic number of cubic graphs. So if you ask what happens for graphs with a higher genus, then we may observe similar behavior but maybe different exponent. So let me summarize my talk. At the end, I want to give you one conjecture. So in this talk, we have seen the so-called universal critical behavior of phase transition in random graphs with width of n to the 2/3, which can be observed in various random graph models. And this takes place when the largest component is formed, which means when the number of edges is around n/2, plus minus some constant times n to the 2/3, or negative infinity or whatever. And then we have seen a kind of random graph processes, which is kind of modern. It is indeed very hot now. Many people are working on this type of process, in particular due to the new proof of the Ramsey lower bound of the Ramsey number R3T using triangle preprocess. One of the models is the so-called Bowman-Fritz process, and the interesting thing is the method indeed. So I have developed a new method combining two kind of separate method, and advantage of doing that is you can determine very fine behavior of component sizes. Then we have seen again strange two critical behavior in a random planar graphs. One with window of width of order n to the 2/3, and the other one with window width of order n to the 3/5. So are there any questions? So if not, I already told you that I want to give you one conjecture on this topic. So due to four-color theorem, we know that planar graph is four-colorable. And as you might guess, if you look at the random planar graph, some planar graphs are sparse, some planar graphs are dense. And if we have very few edges, maybe this can be three-colorable, right? Or even two-colorable, whatever. So there is a conjecture by Tomasz Uchak and myself that for the chromatic number of PNM, there is a threshold for the chromatic number being 4. So threshold function this property, we claim that when m equals n plus theta of n to the, again, very strange exponent, 7/9. So what do you think that what kind of a structure force us to use four colors? So given a planar graph, what kind of substructure makes this number of colors? It's, remember, in this range, the planar graph is relatively sparse. We can go up to 3 times n, right? So anyway, planar graphs are sparse, but in terms of that I, this is very sparse. It's not up to 3n. The thing is the appearance of the k4s. Once k4 appears in the graph, we claim, maybe you might have another argument. Once you see a k4 in the graph, then we should use 4, otherwise 3 colors are enough. Doing kind of heuristic computations, we could see this number, 7/9. But some more structural properties are missing to confirm our conjecture. So if you are familiar with the planar structures and randomness, this might be indeed very good problem to work on, because the groups in Oxford, like Colin McDiarmid and his colleagues, have been attacking this type of problem, but not having exact threshold function, but of that type for many years. So, yeah. Are there questions or not? If not, thank you very much for your attention.